So, welcome everybody. Today's talk is given by Dale, and I'll let him introduce it.
Okay. Do I get to share the screen? I guess so. Today I'm going to talk some more about braids. In particular, I'm going to focus on the discovery by Patrick Dearnois that the braid groups are left orderable. I think that's quite an amazing discovery, right up there with the proof that braid groups are linear, in my opinion. And so I'll begin by giving several points of view of the braid group. And then I'll switch to Patrick's theorem and its consequences. And this talk is dedicated to his memory. He unfortunately passed away last September from stomach cancer. Now let's see if I can get.
Hi, Sophia.
Whoop. Oh dear.
Hello, how are you?
You're not
Good
supposed
to see
be
everyone.
Green.
Hello, Sophia.
Hi there. Good to see you all.
You're out of focus.
Excuse me?
You're out of focus. Oh, well,
Can you see my slides,
yes.
Yeah,
people?
that's it. Yeah.
Okay. Not sure I can. Okay. As I said, I'm going to talk about ordering of braid groups, but I'll start out with several ways of looking at braids. One is strings up in 3 dimensions, up to deformation. Roger's already discussed that, and can also be thought of as a fundamental group of a certain configuration space of points in a plane, which we'll take the complex plane as a model because that's useful. Hello? Someone have a question? Oh. And the third point of view is the braid group as a mapping class group of a punctured disk. So the braid group on end strings can be thought of as strings in 3D, which we'll think of as a complex plane across 0, 1. And on the one end, that set of strings will end at the integers 1 up to n cross 0, and on the other end, the similar set cross 1. And 2 braids are considered equivalent if you can deform one to the other at all times staying in the family of braids. So they have to be embedded, and each slice of the complex plane meets it in endpoints. The product is by concatenation and then rescaling. And I'll recall that the generators look like this. I like to draw braids horizontally because we do algebra horizontally usually. And on this side we have, is my pointer working? Can you see this?
Yeah, yeah.
Yeah.
It all goes. Yeah.
This is the sigma I, the generator sigma I, and this is its inverse. They really do cancel, as this little picture shows. If I and j are far enough apart, the sigmas commute. And then if they're adjacent, I and I plus 1 obey this nice so-called braid relation. Reidemeister move number 3. And Arden showed over a century ago that these relations actually suffice to define the braid group abstractly as a group of those generators, sigma 1 to sigma n, subject to those relations that I just mentioned. Now, another point of view, if we think of the interval as parameterizing a set of n points in the complex plane, let's let delta be the so-called fat diagonal, the set of all n tuples where there's a repetition. Then the pure braid group can be thought of as a fundamental group of that space. You can think of it as also a hyperplane arrangement. Zi equals Zj defines a hyperplane in complex n space. And we look at the complement of that arrangement. That's the pure braid group. And the base point is this vector 1 up to n. And since we removed fat diagonal, the symmetric group acts freely on what's left. It takes a point to a different point. Symmetric group acts by permuting the coordinates. And so we can form the quotient space, and the quotient map is an n factorial fold covering space. And the full braid group is the fundamental group of that quotient space, where we think of the vectors now as unordered because it's an orbit under the symmetries. And of course, in covering space theory, we have the fundamental group of the upper space is a subgroup of that of the lower space, and the quotient is a symmetric group. We have this familiar exact sequence from that point of view. Now it happens that these spaces have no higher homotopy groups. One way to see that is to map Cn minus its fat diagonal to one dimension lower by just forgetting the last coordinate. And note that that's a locally trivial fibration. And we can look at the long exact homotopy sequence of the fibration and do some induction and conclude, since the fiber is quite simple, just the complement of n minus 1 points, all the higher homotopy groups are trivial. And in a covering space, the upper and lower space have isomorphic fundamental groups, higher homotopy groups. So also this group is also trivial. In other words, those spaces are Eilenberg-MacLane spaces, or classifying space for those groups. One consequence of that is that the braid group is torsion-free for all n. Because if you have torsion, it's known that the Eilenberg-MacLane space has to be infinite dimensional. And these are not. The left orderability will also imply that. It's a stronger condition, but we'll get to that later. Now, a naive person might think that if you have a subgroup of a group and you abelianize them, that the abelianizations of that subgroup is also a subgroup of the abelianized larger group. But that's not true in this case, certainly. Notice that the braid relation implies that adjacent generators are conjugate. In other words, all the generators of the braid group are conjugate to each other. So if you abelianize, they become equal. So the abelianization map Bn to Z coincides with the total exponent map if you express it in the sigma I, sometimes called the ride of the braid. Another way that is kind of a cool way of looking at it is using this polynomial function concocted by Sylvester, the discriminant. You take the product of Zi minus Zk, where I and K range over all the subscripts of the generators, 1 up to n minus 1, 1 up to n, not of the generators, of the coordinates of points in Cn. And notice that another way of looking at that, notice that each term appears twice. Zk minus Zi and Zi minus Zk are both in there. So you can rewrite this discriminant as the product Zk minus Zi, where I is less than K, squared. But then there's some minus ones in there. In fact, n choose 2. So we have a coordinate of a factor of minus 1 to the n choose 2. And notice the big diagonal is nothing more than the preimage of 0 under this map. And the map is also invariant under the action of the symmetric group, so you can think of it also as mapping the Cn minus delta quotient by sigma n also to the non-zero complexes. Now, an interesting observation, I won't go through the proof, it's just a calculation. The induced map on fundamental groups is exactly the same as the abelianization. Fundamental group of this is Z, fundamental group of this is the braid group. And the induced map on the discriminant gives exactly abelianization. It's also locally trivial fibration, and it's fibers that connect the space whose pi1 is the commutator subgroup. Of course, the kernel of the abelianization is the commutator subgroup. You can also use a discriminant to see that the abelianization of the pure braid group is isomorphic to Z to the n choose 2, and how that abelianization relates to the abelianization of Bn, which is much smaller. Okay, so we have this curious fact that even though the pure braids are a finite index subgroup, their abelianization is much larger in general than the bigger group. Now, a third point of view is mapping class groups. If you keep track of those points moving around the complex plane and extend that motion to an isotopy of the plane itself, beginning at the identity and ending at a self-homeomorphism that permutes these the base point, the coordinates, as I said here. It's also convenient, instead of looking at the whole complex plane, to just take a large disk which contains the base points. Let's say the round disk with diameter, the real interval 0 to n plus 1. And the set here is the base point. And we have, or we can think of it as a set of marked points or punctures. And we can realize the braid group as the mapping class group mod Dn, where Dn is the disk in the complex plane with n marked points. And that's also a useful way of thinking of the braid group. And now let's discuss the ordering. Let me first explain how I got interested in it. I was working on a conjecture by Joan Berman, who, this was in the 90s. She considered singular braids where the strands can intersect, but only in double points. And so if you include these singular braids, you get a larger algebraic object, no longer a group because these aren't invertible, but we get something called the singular braid monoid, SBN. It's not quite the same as welded braids, but similar idea. And Joan, at the time, Vasiliev invariants were being worked out, and Joan wanted to look at these in terms of the braid group. So she suggested mapping this larger monoid into braids by taking sigma I to itself and tau I to the difference between sigma I and sigma I minus 1, sigma I inverse. Well, this doesn't make sense in the braid group, but we have to extend the braid group to the group ring with integer coefficients. So for this to make sense, the target is not the braid group, but the group ring, ZBN, where you take formal linear combinations of braids and add them in an obvious way and multiply them as if also in an obvious way. So it becomes a ring. And her conjecture was that this map is injective. In other words, the singular braid monoid can be thought of as a submonoid of this ring. And working on this with a student named Zhu Jun, we would do calculations in here and would sometimes need to cancel multiplicatively. For example, say if AB equals AC, then B equals C. But of course, that's not necessarily true in a ring. If there's zero divisors, this implication is not necessarily true. You see, start and say A times B minus C is 0. But if A is a zero divisor, we could have both of these be non-zero and still the product be 0. So we had to check that we weren't canceling zero divisors, and that wasn't always so easy. And I wondered if there were any zero divisors in group group rings ZBN. And when I learned about Darenois' result that BN is left orderable, I also learned that left orderability implies that the group, if a group is left orderable, then its group ring does not have zero divisors. This is conjectured to be true for torsion-free groups, but amazingly, it's still an open question. It's been around since the 1940s. I think Kaplansky raised that question.
Sorry, what's the question?
Pardon?
What was the question?
Oh, if the group ring of a torsion-free group has zero divisors.
Right.
It's not known. If there is torsion, you can get a zero divisor by, let's say, a group element little g has g to the n being the identity. Then if you look at the polynomial g minus 1, or at the group ring element g minus 1, that's a zero divisor because that times 1 plus g plus the g to the n minus 1 multiplied by 1 minus g gives 1 minus g to the n, which is 0 if g to the n is equal to 1. So if there's torsion, you do have zero divisors. If there's not torsion, in general, it's still unknown, amazingly so. Well, alas, we didn't prove Berman's conjecture. Louis Paris, a few years later, settled it and did prove that it's true. But, well, let me now say a few words about left ordering. What is a left ordering? It's a strict total ordering of the group elements such that multiplication on the left preserves the ordering. So if G is less than H, then FG is less than FH. A lot of algebraists consider right orderings of groups. A group is right ordered if and only if it's left ordered, but by different ordering. And more classically, two-sided orderings which are invariant under multiplication on both sides, had been studied. That was the classical idea of an ordered group. It's a much stronger condition. And anyway, Derenwat chose left ordering as the goal. So let's look at left orderings. If you look at the set of all group elements bigger than the identity, we call that the positive cone. It's easy to check that for any group element, it's either in P or its inverse is in P, or else it's the identity. And also the positive cone is closed under multiplication. So you get this nice partition of the group into two sub-semigroups, the positive cone and the negative cone. Product of two guys less than the identity will also be less than the identity. And conversely, if you have a subset P of a group satisfying these two conditions, that defines a left ordering by saying that G is less than H if G inverse H belongs to that set. It's quite an easy exercise to show that that's transitive and left invariant. So Derenwat defined an ordering on Bn in the following way. You say a braid is sigma I positive if it has an expression in which sigma I occurs with only positive exponents, and I is the lowest generator that appears in the expression. No sigma j appears for j less than I. And if a braid is sigma I positive for some I, then we'll call it sigma positive. And it's easy to see that two sigma positive braids will have a sigma positive product, more or less direct from the definition. But the hard part, Derenwat proved the very amazing fact that every braid is either sigma positive or its inverse is sigma positive, or it's the identity. And once you've got these two facts, then what I said on the previous slide implies that we have a left ordering of the braid group. It's actually a very useful and interesting ordering, but let me just discuss an example here. Consider this braid, sigma 1, sigma 2, sigma 1 inverse. Well, it's not sigma 1 positive because we've got this -1 here. And its inverse, which you get just by reversing the orders and negating the exponents, is also not obviously sigma positive. But the braid relation, here's a picture of the braid beta, sigma 1, sigma 2, sigma 1 inverse. If you take this middle strand and move it up, like this. That's an isotopy through braids. And now we get a word, sigma 2 inverse, sigma 1, sigma 2, which is sigma 1 positive. Therefore, our braid beta is positive in Dearnois ordering. This procedure actually can be generalized to give an algorithm for finding a sigma positive or sigma negative expression for a braid. You take consecutive plus and minus signs in the lowest strand that acts in there, and then just move that strand up. So the ordering is simply alpha is less than beta if alpha inverse beta is sigma positive. Now everyone now calls this the Dearnois ordering. Patrick called it the sigma ordering. And he proved that theorem on the previous page. In passing, in a paper in 1994, which he said his main goal in that paper was to prove that that there's an algorithm for deciding whether an identity is or is not a consequence of this leftist distributive law, x times yz equals xy times xz. He was a set theorist, and he was looking at elementary embeddings in set theory. And that's what motivated this question. And the fact that the free left distributive system on one generator is orderable in a similar sense was the motivation. And I'll quote Dearnois here. The first proof of that actually used an assumption of very large cardinals, which can't be proven from Zermelo-Frankel set theory, but may be consistent. So to quote Dearnois, he says, the linear ordering in the braid group has been derived from a linear ordering of the free left distributive system with one generator. The first complete proof of the existence of the latter ordering occurred in a paper by Richard Laver, about large cardinals, and a large cardinal axiom from set theory was explicitly used to prove the ordering's irreflexivity, or the absence of a cycle for the left divisibility relation. This gave rise, of course, to the question of whether a large cardinal axiom was needed. And actually, it's not, as we shall see. The point here is that considerations of highly infinite objects, elementary embeddings, had led to an intuition that ended in results of the most constructive spirit. For example, a new algorithm for braid word comparison. I actually met Patrick in the late 90s, trying to understand his proof. And right after that meeting, I was at a topology conference organized by Roger in Sussex and gave a talk on Dearnois' theorem and confessed that I didn't really understand the theorem that every braid or its inverse is sigma positive. And anyway, a bunch of my colleagues, including Colin here, and Roger and Bert Wiest, and a few others, we started kicking this idea around, and took a couple of months, but we finally did find an alternative proof that was a little more topological. And I'll discuss that now. It uses the interpretation of the braid group as a mapping class group, mod DN. So remember, we were looking at the model of the disk as being a large disk in the complex plane. whose diameter was the interval 0 to n plus 1. Now, a mapping class is defined only at the isotopy fixed on the punctures and on the boundary. But if you look at the image of the real axis, you can insist that the image have sort of minimal intersection with the real line itself. Let's look at some examples here. For example, here's the case n equal 3. I got the points 1, 2, 3 in the complex plane. This is the disk whose diameter is the interval 0 to 4. And the map sigma 1 takes this point, moves it this way, takes this point and moves it that way. And the end result, we see the image of the real line goes up here, and then back across itself, and then down here, and then across. And now if we apply another braid, let's say sigma 2 inverse, then I want to touch the screen with my fingers, but I know you won't see that. That will take this point and move it this way, and this point will move that way. So we see the end result has scrambled the real line a little bit more. It goes up and then down in the lower half plane, over to number 3, then back in here, and so on. So these are what we call curve diagrams for those braids. Simply the image of the real axis under the action of the braid on the disk. Whoop. So the dichotomy to define the positive cone is to take the positive braids to be exactly those for which the braid diagram, reading from right to left to right, departs the real line above rather than below. So if the imaginary part that first becomes non-zero as you go from left to right becomes positive, then we'll call it a positive braid. And remarkably, well, it's not hard to see that this gives the dichotomy. Every braid is either going to have its curve diagram go up first or down first, unless it's the identity. That's quite obvious. But amazingly, this is exactly the same as being sigma positive in Desarnois' sense. Takes some work to do that, but it does give, I think, a nice picture of what this ordering really means. Now let's discuss some of the properties of this ordering. It actually happens that there are many possible left orderings of the braid group. Not only an infinite number, but uncountably infinitely many. It's a nice theorem of Peter Linnell that a group either has the set of left orderings of a group is either finite, possibly 0, or uncountably infinite. There are no groups that have exactly countably many left orderings, although there are for two-sided orderings by a theorem of Buttsworth. Anyway, let's get back to Desarnois' ordering. It's a discrete ordering, meaning that positive cone has a least element, namely sigma n minus 1. You can see that by observing that, of course, sigma n minus 1 is sigma positive. But if there was a braid between it and the identity, you can conclude that beta inverse sigma n minus 1 is also sigma positive by definition. But beta inverse must be sigma negative because beta was sigma positive, right? So this combination Well, if it were sigma I positive for I less than n minus 1, then this guy would be negative, not positive. But we're assuming that it's sigma n minus 1 positive, so beta must indeed be a power of sigma n minus 1. And that gives a contradiction. All the other powers, positive powers of sigma n minus 1 are bigger than it. So we do have a smallest positive braid. We have a largest negative braid. You can see that simply by the above. And so every braid has an immediate successor and predecessor in the ordering. That's what a discrete ordering can be thought of. Amazingly, certain subgroups with the same ordering become densely ordered. That to me is kind of counterintuitive. Have a subset of a discrete set being dense. It's but in fact true. Theorem. I actually discovered this theorem I was high on oxycodone because I just had a hip replacement. And somehow this theorem came to me that the commutator subgroup does not contain a smallest sigma positive element. Okay, it's remember the commutator subgroup is fairly large. The quotient, the abelianization of Bn is infinite cyclic. So this is infinite index. If it were finite index, it would be ordered discretely. But it amazingly has no smallest positive element in the Darnois ordering. And there's other interesting subgroups that have that property too. For example, the kernel of the Barreau representation, which we know is got a non-trivial kernel if n is at least 5, that also is densely ordered by Darnois ordering. I'm not sure what this tells us beyond just a curiosity. Pure braids, as I said, that's a finite index subgroup that does have the smallest positive element, namely the square of the smallest sky in the braid group. That's a pure braid. And it actually happens that the pure braid group can be given a strict total ordering, which is invariant under multiplication on both sides. There are several ways to see it. One is to express it as a semi-direct product of free groups, and you can order free groups by two-sided orderings. Another way of seeing it is it's known that it's residually nilpotent. If you look at the lower central series, it never terminates, but it does have its infinite intersection just being the identity group. So you look at the successive quotients of the lower central series, those are abelian groups, torsion free, and you can order them with a two-sided ordering and then use the ordering of those quotients to order the pure braids. Anyway, pure braid group has a two-sided ordering, but I claim that Darnois ordering cannot, except for n equal 1 or 2. And let's look at this example. Beta is sigma 1, sigma 2 inverse. Gamma is sigma 1, sigma 2, sigma 1. And it's easy to check that if you conjugate beta by gamma, you get beta inverse. I'll leave that as an exercise. That implies that for n at least 3, the braid group can't be given a strict total ordering, which is invariant under multiplication on both sides. Because if beta is positive, its inverse is negative, But a two-sided ordering is invariant under conjugation, so you would get a contradiction if you can conjugate beta to its inverse, if beta is not the identity. But we do have such an equation as we've seen here, as long as we get at least 3 strands. In fact, even more is true. There's no compatibility between a two-sided ordering of the pure braid group and a left invariant of the full braid group. That was proved independently by myself and Akbar Remtola, and also a couple of Russians. The names will come to me in a minute. Now let's look at the so-called positive braid monoid. That's all braids that express in the sigma I using no negative exponents. That's, in other words, the monoid, if you look at the usual presentation for the braid group and just consider that as a presentation for a monoid, you get Bn plus. And Roger explained many moons ago that this embeds in Bn in an obvious way. Well, if you restrict Desarnois' ordering to Bn plus, it's actually a well ordering. A well ordering is one in which every non-empty subset has a smallest element. And it's actually quite a large ordinal. The well ordering that has order type omega to the n minus 2. So as soon as n is at least 3, it's quite a big ordinal. And now let's get to some applications to the theory of knots, which is the subject of this series. And of course, the main connection between the braid groups and knot theory is taking the closure, beta hat. You take all strands on the left and connect them to the strands on the right, the points by curves that do not cross each other or the braid. So remind you that Alexander proved about a century ago that every knot or link can be realized as a closure of some braid, typically in many different ways. Now I'll remind you of the Garside element. You take this braid, you can think of that as the full twist. You take the end strings and twist one end 360 degrees, then you get the nth power of the braid sigma 1 up to sigma n minus 1. It's the Garside element is a little different. This is the square of the Garside element. And it's a pure braid. It commutes with all braids. And in fact, it's the generator of the center of Bn, which is infinite cyclic. And its powers are cofinal in the Desarnois ordering of Bn. Here's the Russians I mentioned. This is a different pair of Russians. These guys showed that every braid far enough from the identity actually has a very nice closure. In particular, you're not going to get the trivial link. Or, well, here's the theorem. Suppose n is at least 3, and you have a braid beta which is not between delta minus 4th and delta to the 4th. So it's not in that interval with respect to the Desarnois order. Then its link closure is prime. It's not a connected sum of two knots or links. It's a non-split if it's a link. and is non-trivial if it's a knot or a link. So it's only braids in this interval that can give you, for example, examples of non-trivial braids whose closure is the trivial link or trivial knot. I think that's a quite interesting result. Another application by Tetsuya Ito is to consider the braids as mapping classes, and there's a well-known classification of mapping classes, which in this case, well, every mapping class is periodic, reducible, or pseudo-Anasov. I won't digress into the definitions. I think most of you have seen this before. And Ito showed that these properties of braids actually pass in a very simple way to the properties of the knots or links that are formed by the closure. His theorem is that if you have a braid, an end braid, n is at least 3. I think that's required. Maybe it's true also for 2. And if its closure is a knot, and beta again is not in this interval, the same one as before, then beta hat is a torus knot exactly when beta is a periodic braid. It's a satellite knot exactly when beta is reducible. And in all the other cases, hyperbolic knot, if and only if beta is pseudo-Anasov. So this is, I think, another very interesting observation regarding the ordering and how things far enough from the identity in the Desarnois order behave in a very predictable way. Ito also gave a lower bound for the genus of a knot. He proved this theorem. If n is at least 3, then beta is not in this interval between delta squared to the minus m and plus m in the Desarnois ordering. And if the closure is a knot, then the genus is at least m minus 1. So it gives a lower bound for the genus of knots that are far from the identity. And a very recent result, I saw it in the archive 2 or 3 months ago, I think it was announced. Feller and Hubbard, this I think is the daughter of the famous Hubbard, proved the following theorem. It gives a lower bound on the so-called braid index. If you have a link, an interesting question, you can express it as a closure of a braid, but you want to know what's the smallest number of strands for which that's possible. That's called the braid index of the link. And they give a connection between Desarnois ordering and the lower bound of the number of strings. Namely, if you have a integer at least 2 and a braid not in this interval between the positive and negative nth powers of delta squared, then the closure cannot be expressed as the closure of a braid with fewer than n strands. So this gives a way of concluding that n is, if n happens, if your braid, an n braid happens to be outside this interval, then you know that it's a minimum number of strands. That had been conjectured by these Russians, but only recently proved. That's it. Thank you, folks, for listening. There are more things that I could say, but my time is just about up. It's been 50 minutes, I guess. And if anyone has questions, I'm happy to.
Okay, so has anybody got questions for Dale? I can unthingamy everybody. Unmute all. Yeah. Any questions?
Thank you very much.
Thanks, Dale.
Yeah, my pleasure.
How the hell have I forgotten all that stuff?
Well,
Yeah.
I have a number of questions, Dale.
Okay.
This the paper you wrote with Zhang, was that the one which I was involved with as well?
No, I think that had to do with centralizers.
Oh yeah, right. So long ago. Yeah,
Yeah.
yeah, yeah. That was That, and that, but there wasn't a consequence of that. Was that for n less than or equal to 3, the Berman conjecture was true? Wasn't that a consequence?
I think that's right. Yeah.
Yeah.
So we couldn't push it beyond that. And,
No, we were stuck, weren't we?
yeah.
Can you switch just to gallery view so we can see everybody?
Sure.
Yeah, I'll take
out the sharing.
Stop share. Yeah.
Right. Okay. And gallery view. There we go. Okay.
There's a lot of invisible people here.
I don't know if this is a silly question, but is the singular braid group orderable? Because you can make it into a group. It doesn't have any torsion.
So you just introduce inverses to those towers?
Yeah, and it embeds, the monoid embeds Colin and I.
Right.
Together with Jordan.
You call that the braid permutation group, wasn't it? You can think of it as a subgroup of the automorphism group of free group.
No, that was the weld group, but that's got torsion.
Oh, that's the weld.
Yeah.
The braid permutation group. Okay.
No. Anyway, something to think
I have
about.
to think about that. I don't know.
Yeah. Okay. Do you have actually the braid groups are linear? Do you have a reference for that?
Kramer and Lawrence.
Bigelow and
Is it Bigelow?
And also
Kramer.
Kramer, yeah. Dan Kramer.
Dan Kramer.
He's at Warwick, I believe. Isn't he, Colin?
Yeah.
Perhaps we ought to put that in Lou's basket of stuff. That reference.
Yeah. I think the title is Braid Groups Are Linear.
Yeah. So that should be easy to find.
Yeah.
There's a charming movie of Patrick where people rediscover the ordering of the braid group. If you haven't seen it, it's quite cute.
Mathematician in Paradise?
Yes.
Yeah.
Hi, Dale. I have a question.
Okay.
I'm invisible, but hopefully you can hear me. Thanks for your talk.
You're welcome.
Does this sort of stuff work with the other finite type Artin groups that also have Garside elements? Or maybe just the type DN and the BN ones that kind of have mapping class group ways of describing them as well? Or is it a very Brady thing?
I don't know
BN
that.
is a subgroup of usual braids, so no problem.
What?
BN is a subgroup of usual braid group, so you can have ordering.
Uh-huh.
Okay, so it's just, okay, so you take the symmetric, you look at it as a subgroup on two end strands with some certain.
Yeah, the first element is sigma 1 squared, so this gives you the type B as a subgroup of standard braid group.
Uh-huh, yeah. But the other Arden groups, the so-called spherical Arden groups, I guess.
Yeah, I guess they're the ones with the Garside elements.
Yeah, I don't think that this sigma positive argument will work in general for those guys. I don't know. Are they all torsion free?
Yeah, I think so.
Arden groups?
Not all. Well, it's a conjecture that all Arden groups are torsion free, but I think it's been shown for the finite type ones.
Uh-huh. I don't know what orderability properties they have. It's worth looking into. Who am I talking to?
Rachel Boyd.
Rachel.
Hello.
I'll get in touch with you if I think of anything.
Great, thanks.
Good. Are there any more questions? And Dale, that's your talk, is it? You don't want to give another one, or?
No.
No.
Not, but I'd love to hear other people give talks.
Well, I think Scott has continued. Is that correct?
Yeah, I'm ready whenever you are.
Do you want to give a talk next Friday? I guess Lou is going to continue on Tuesday. Yep.
Yeah, sure. That'll be fine.
Oh, Lou, I tried to hook into your seminar yesterday. I was 5 minutes late, and I had to wait forever to be admitted.
Oh, sorry. I went into share screen and I didn't see you. Yeah.
Yeah. So I missed your seminar yesterday, unfortunately.
I'll try to rectify that somehow next time.
There's a way of eliminating that problem, and that is to just not have a waiting room associated with Zoom. Uncheck the waiting room.
How do you eliminate the waiting room?
You just go to the security button and then
somewhere, I'm not sure where it is. There's a way of
there's a list of things, and on the left is security, and if you click on that, one of the things you can do is to get rid of the waiting room, so people automatically come straight in.
I'll do it.
Yeah.
I'll do it.
That means anyone can enter the.
Well, only if they've been
Darth
given
Vader included.
Yeah, that's why no Tom, Dick, or Harriet can get into this talk unless they've been invited. So.
No riffraff, right?
Well, no, I think we've got a bit of riff. Bit of hoi polloi. Okay, well, many thanks, Dale. I think a round of applause.
Yeah, thanks, Dale.
And the next talk will be on Tuesday, and Lou will continue. And then on Friday, it's Scott, who's going to talk about something which seems very intriguing.
It's a categorical description of embedded surfaces in free space.
I'm already lost. Okay.
Right, well, I'll try to make it all.
Superficial categorification.
Yeah.
Okay, well, I'll
Looking
end
forward.
everybody now. Keep safe, keep well. See you on Tuesday.
Bye-bye.
Bye.
Right.
Thank
Bye,
you.
everyone.